But what if we're an attacker? Think maliciously. What if the arguments don't match up? What if I provide 2% symbols, but only one argument? Well, then weird things start to happen. And when weird things start to happen, that's where the attacker can start doing weird things and making malicious things happen. So here's an example where printf works properly, and then we'll think about what happens when it doesn't work properly. So this function, it doesn't do a lot. It has a secret value called 40 that we assign to 42, and then it says printf %d. And remember, when we have a percent formatter, we match it up with an argument. So this says, please print out, well, I don't know what you want to print. I want to print %d, and I'm going to substitute that with the second argument, which here happens to be the number 1, 2, 3. What does this look like in the stack? Well, I could draw a stack diagram, and the stack diagram says this is a function, so it has an RIP and an SFP. All functions have those. When I call a function, I get these two saved values on the stack. Then I declared a local variable secret. That shows up on the stack too. And then it's time to call printf. And remember, what's the first thing you do when you call a function like printf? You push the arguments onto the stack. So I push the number 1, 2, 3 onto the stack. There it is. It's an argument to printf. And then I push this string, %d new line, onto the stack as well. And there it is. That's the other argument to printf. And remember in C, strings are a pointer to the first element of a character array. So that's why I have here an address, and it points at %d new line. Not the most important detail here, but that's how you represent strings in C. And then printf starts to execute. Printf has an RIP SFP like every other function, and it has its own stack frame that we don't really care about. So this is what the stack looks like when printf works as intended. And what happens is, well, we don't really know what printf is doing, but you can think of what printf is doing as it reads this first input one by one. And it sees a % symbol, so it says, I got to go on the stack, find the next argument, and substitute that argument into the %d. So what does printf do? It goes on the stack, it looks for the next argument, which happens to be 1, 2, 3, and it prints out 1, 2, 3 in place of the %d. And then it prints the new line. So the resulting output here would just be 1, 2, 3, to make a long story short. But the important thing is that printf had to look on the stack. And printf thought to itself, OK, well, the first argument that was provided to me was this one. That's just %d new line. That's the very first argument. Here I'm going to start calling it the 0th argument, arg0, and that's the first string that you pass in with all the % formatters. And then because there was a %d, I will go to the next value on the stack, which happens to be 1, 2, 3, and print that out to substitute it with the %d. So this is what it looks like when things work as intended. But what if the arguments don't match? Well, then we get something malicious. So if the arguments don't match, then we might have something like this. This is another printf call, but this time, instead of providing an argument to match with the %d, I don't provide an argument. This is an incorrect call to printf. So what's the C compiler going to do? Of course, it's going to just compile it and hope that the worst doesn't happen, because thank you, C, for not doing any checks. So what's going to happen? Well, again, we get the same stack as before. The only difference is when I push arguments to printf, I no longer push 1, 2, 3, because that's not an argument. I only push a single argument, arg0, and that happens to be a pointer to the %d new line string. So there's just a single argument to printf. I push that argument. Printf has its own RIP, SFP, and its whole stack frame. So now what happens? Well, once again, printf starts reading its 0th argument. That's the very first thing that I pass in with all the % formatters included. And it reads this character by character, and it sees a %d right away. And it thinks, aha, it's a %d. This means I should go on the stack, find the next argument, and substitute that into the %d. So what will the program do? It will go on the stack. OK, well, here's argument 0. That's the string that I'm currently reading. I go 4 above that. This must be argument 1. So I'll just take this value, substitute it into the %d, and print it out. So what will this code print? It will print secret. It prints out the secret value that we didn't want people to know, because it's secret. So the punchline here is because the arguments were mismatched, but the C compiler didn't know that they were mismatched, what happened was when the printf function saw the %d, it went on the stack to look for an argument. There is no argument. We didn't push one. So it instead finds some other value, like a secret value or some other sensitive value, and prints that out instead. So this code prints out 42 when it's not supposed to. This is the key idea behind all the exploits that we're going to see next time. They all involve printfs and having a mismatched number of arguments. So kind of the key takeaways from this section, when you call printf, the very first argument, which I will now call arg0, or the 0th argument, this is always some hard-coded string. And remember, strings are addresses to the first byte of a character array. But basically, this first argument, or 0th argument, is always a hard-coded string. And the hard-coded string has % symbols that will be substituted with placeholders. And if this first or 0th argument mismatches with the number of arguments that you provide, well then the printf is going to look on the stack anyway for arguments, potentially leaking things that you don't want to leak. So this is the key idea that we're going to continue exploring in the next video.